In the previous section, Arne talked about deep neural networks and how we can construct these powerful and complex models from simple computational units. And now it's time to look at the applications of these complex models in the real world, and specifically, we are going to talk about computer vision. Computer vision is one of the domains that deep neural networks have been widely used in. Here you see some examples of the common tasks in computer vision. For instance, on the top, we have a model that takes a video as input and identifies the objects in the video. And you can imagine this could be useful, for example, for self-driving cars to avoid bumping into objects. And on the bottom, you see some more examples, including detecting and segmenting objects in images. So generally, the tasks in computer vision involve some visual input, either images or videos. Now let's see how we can represent the images so that our models can work with them. Here we have a grayscale image, and in order to use it as input to the model, the first step is to turn it into numbers. So what we can do is to assign a number to each pixel, and usually color values are either between 0 and 255 or between 0 and 1. In this case, we have numbers between 0 and 255, 0 being black and 255 being white, and everything else is between these two numbers. Once we assign these numbers to our pixels, then we have a matrix, and now we have a numerical representation of the image which we can use as input to the model. The same thing goes for colored images, except that in this case we get a tensor because we have 3 color channels, red, green, and blue. And so we need to create a matrix for each color channel, and then putting them together gives us a tensor. Now that we have a numerical representation of our image, let's go ahead and use them as inputs to our neural networks. But can we simply use the standard neural network that Arne talked about in the previous section? And the answer is, of course. What we can do is to pass each pixel as a different input dimension to our model. And that means that we would have a weight connection from every pixel in the image to every unit in our first layer. Just to show you, here is a visualization of how many connections would that be only for the first unit. To simplify the visualization, from now on, instead of showing all the weights, I'm just going to use a box and 4 arrows. So here we have the weight connections between all pixels and the first unit, and then we have the same thing for the second unit and the third unit, and so on. While in theory this is possible, there is a problem. And the problem is that there is just a lot of weights, in other words, parameters in this model. For example, if we have a 200 by 200 image, and say we have 50,000 units in the first layer, then we have a model with around 2 billion parameters. And we neither have enough training samples to train a good model, nor we have the memory to store this model. So then the question is, how can we reduce the number of parameters while still having a good model? One source of inspiration is the observation that complex patterns emerge from simple local features. Let's take a look at this picture of a zebra here. While the pattern in the complete picture is rather complex, this complex pattern actually is constructed by simple local features. So maybe instead of looking at the whole picture, the units in our model can learn simple local features and then combine them to identify complex patterns. Another source of inspiration is the visual system in the brain. And scientists have identified some time ago that neurons in the primary visual cortex are responsive to simple local features. And yet, we are able to perform visual tasks such as object detection and object recognition nearly perfectly. So, focusing on simple local features seemed like a good idea. So instead of having weights from all pixels to a single unit, let's change the model such that the unit only looks at local information. I'm going to change the circle into a box and also remove the arrows to simplify the visualization. So now we have a single unit that only gets weight connections from this local area. In other words, it is sensitive to local feature at this specific position. But ideally, we want to identify this feature at any position in the image. To do that, we can simply slide the same set of weight connections across the image and get new units. So we slide it 1 pixel at a time, and that would give us another unit that is sensitive to the same feature, but at a slightly different position. Slide it again, gives us another unit, and we continue sliding 1 pixel at a time until we cover the whole image. And the operation we just performed here is called the convolution operation. Basically, it's sliding a set of weights over the input matrix to generate a new matrix. And now some terminology. These set of weight connections are commonly referred to as a filter or a kernel, and the output of the convolution operation is often referred to as the activation map or a feature map. Now, remember that the main motivation of using these local weight connections was because our original neural network had too many parameters. But how many parameters do we have now? You may be surprised, but for the operation we performed here in this slide, assuming that we use a 3x3 filter, we only have 9 parameters. And this is independent of the number of units because we are using the same filter but at different positions in the image. So the units in our activation map use the same weight connections, they're just sensitive to different locations in the image. So looking at local information paid off in terms of number of parameters, but also in terms of performing complex tasks, convolutional neural networks perform very well and they dominated computer vision for a long time. So we have a model with less parameters that also performs very well. Now let's take a look at some examples of the convolution operation. We have the zebra picture again, and I have a 3x3 filter that looks like this. Now, if we perform the convolution operation with this filter on the zebra image, how do you think the activation map looks like? And this is how the activation map looks like. So what our filter in this case is doing is basically edge detection. And also note that it is detecting edges that are parallel to the pattern in the filter itself. So basically vertical edges. Now what happens if I transpose this filter and convolve it with the image? As you might have guessed, this filter is sensitive to horizontal edges now. And we can also see that in the activation map, that the horizontal edges are more prominent than the vertical edges. Okay, so far we learned about convolution operation, we also learned about filter and activation maps. But how do we create convolutional neural networks? Well, basically use more filters and more layers. So let's create one together. We have our image here, and let's go ahead and convolve the kernel with it. Covering the whole image, and that results in a single activation map. And the next kernel would give us another activation map. And so on. We can use as many kernels as we want and get activation maps in our first layer. But before we move on to more layers, I want to introduce another terminology, and that is channels. Channel is basically same as the activation map, but it is mostly used to talk about dimensions. So for example, here we have a tensor with a specific height and width and 4 channels because we have 4 activation maps. All right, now that we have a tensor, let's represent it with a cuboid and move on to get our second layer activations. But how does the kernel look like here? Well, remember that when we were generating the activation maps for the first layer, our image was a matrix, and so we simply used a 3x3 matrix as the filter to generate the activation maps. But going from layer 1 to layer 2, we have a tensor as input, not a matrix anymore, so our kernel should also be a tensor. It is still local, but it should span all the channels. Besides that, the convolution operation itself is exactly the same. We start from the top left corner, and we have a weight connection from all channels to this single unit. And as before, we slide through the image to cover the whole image. And that gives us a single feature map in the second layer. And then you apply another kernel and get another activation map, and the story continues. And that is basically the gist of convolutional neural networks. Colors are represented as numbers, and the key characteristic of convolutional neural networks is the convolution operation, which allows the model to identify complex features while saving parameters. I hope you enjoyed this section, and see you in the next one.